the questions about consciousness in the context of evolutionary biology. He recognizes, as sometimes we're apt to forget, that the human brain is an evolved structure, and that it came from brains that were somewhat simpler. And one of the really remarkable things I think that's happened in evolutionary neurobiology over the past 15 or 20 years is that we realize how very, very conservative nature is. And that structures don't come into being sort of full-fledged and magnificent, but that they conform to the principles that were, as it were, stumbled on by Mother Nature very early on. And so we find at some levels that there's a great similarity between the way information is handled in the leech or in the fruit fly and in the primate brain. These principles can be somewhat modified and more complicated in the primate brain, but it's really quite striking how very similar certain of these principles are. So in thinking about consciousness, I think that Nick is absolutely right to say that we have to try to understand what those processes serve, such that they could have been selected for in the process of natural selection. And there can, of course, as we know, be funny little things that might come into being morphologically in our bodies and in our brains that weren't specifically selected for and weren't specifically selected against, and so they're there. On the other hand, for something as really sort of significant as the difference between being asleep and being awake, it looks like there have to be precursors to those functions, and hence between the difference between being conscious and not being conscious, there have to be precursors for that in many other animals. And indeed, of course, we know that there are. Now, one of the other things that I think is terribly important about Nick's account, and this really also now plays a very important role in Andy's account, is to recognize that the brain is a dynamical system, and that the previous state of the brain affects the way things are processed in the next state and in the next state and so forth. It also means, and now this has become quite common, I think, in neuroscience, but I think it wasn't when Nick was first thinking about this, is that you can characterize the properties of neurons in terms of a state space. And it would be a multi-dimensional state space, of course, not a two-dimensional state space. But that once you characterize the activity of neurons in a state space, very interesting patterns begin to emerge. And some of these patterns can be characterized, as Nick quite rightly points out, in terms of attractors. So one of the hypotheses that he's going to present to you is the idea that there are attractors of a certain kind that are specifically associated with conscious sensory states. Now, whether that turns out to be true or not is, of course, an empirical question. For there to be states of that kind and states with the dynamical properties that we think essentially all nervous systems have, it's very, very common to see recurrence, meaning that if this is the axon and there's an output there, perhaps to the muscles or perhaps to another neuron, that there will be another branch of that axon that will come back and maybe synapse on the input neuron to that axon, maybe a little bit deeper, or maybe even on that axon itself. And the idea that recurrence, this loopiness, is absolutely essential is, I think, an idea that certainly Nick has, but it's also an idea that's been around in neuroscience for a long time. We see this in Linus, in Jerry Edelman, and Paul, I think, had this idea early on too. Of course, Nick recognizes, as I think we all do, that recurrence is not sufficient. That we see, of course, that there's recurrence in, for example, the worm, C. elegans, which is about a millimeter in length and has only 302 neurons. And it's full of little loops, and we don't really think that C. elegans with 302 neurons is likely to be conscious. And moreover, we know that there are loops in the spinal cord that are still effective, for example, in the knee jerk, even when you're spinally transected so that you can't feel. So recurrence is not sufficient, but it's likely to be an important component. And so what kind of recurrence might be important? What kind of dynamical properties in the system might really be important in understanding conscious behavior? And here I think Nick thinks that recurrence that involves loops back from a motor neuron to a sensory neuron are important. Now, I think that that's likely to be true, but exactly how that story is going to unfold, I think Nick has some early ideas. I think Andy has important ideas about this as well. One of the more sort of general ways that has emerged in neuroscience, and I think Andy's work is a beautiful demonstration of this, is the realization of the fact that natural selection takes very, very seriously, if I can put it anthropomorphically, the idea of prediction. In a certain sense, and Rodolphe Linas, the great neuroscientist, used to say this regularly, is that nervous systems are all about movement. And what drives, and Nick makes this point also, and what drives the evolution of nervous systems to get more and more complicated in their sensory domain, as well as in all those fancy neurons between motor output and sensory input, is prediction. The better C. elegans can predict where the food is, where the mates are, the better it will do. Now, you can't, of course, if you're Mother Nature, you can't directly select for sensory processing or for predictive capacity. All you can select for is whether the animal's behavior outcompetes that of its fellows. But the better your predictions are, the better your shot at outcompeting your neighbors. And so one of the things that we see now in quite simple animals are forward models, the kinds of models that play a really important role in Andy's work. And basically the idea of a forward model is that it has a motor output, but the forward model makes a prediction about what sensory experience is likely to ensue. And many animals have a forward model that's also hitched to an inverse model. So the forward model will predict an output that may actually go to the motor system, and it may also go back to the inverse model that says, that's not quite correct, so you better modify your motor output, and then it goes back into the forward model. Critical to the forward model is a representation of the sensory domain. And depending on the organism, it might be a representation of touch or vision or something else. And that turns out to figure quite importantly in, I think, in Nick's account of what an inner model looks like. Now, the inner models that have been studied in fairly simple animals have, I think, taught us quite a lot. Not necessarily because they shed light directly on the idea of a conscious experience, but because they give us a clue as to how these inner models of the world could be elaborated in such a way as to give rise to something like conscious experience. So one of my favorite inner models, or my favorite recurrent loops at any rate, is in the locust. So the locust, as you know, is a kind of like a grasshopper. And part of its mating ritual for the male is to rub its wings together and make a big racket. And that's meant to attract the females. This is sort of a behavior that's quite widespread throughout the animal kingdom. In any event, when it does that, of course, it makes a racket that it too will hear. So what evolved was a collateral output from the motor system that goes back to the sensory system, and it's precisely timed to suppress the sound of his own wings rubbing. And so you can already begin to see how you can modify the sensory world as a result of these loops. So that's one way of doing it, that is to suppress it. We have many instances in humans as well where the neurons suppress a sensory effect, but they can also augment a sensory effect. Now, I don't want to take too much time because I think Nick's own version of this is probably the best. And I should just say parenthetically that I think his book, Soul Dust, is really so much richer and in a way so much more accessible than the papers because he has time to really lay things out. So if you found that you weren't convinced by the papers or you didn't understand the papers, I would recommend you go back and at least those first 4 chapters have a look at the book. So I want to give you an idea for what a different kind of sensory or internal model of the brain looks like. And I'm choosing this one partly because it's an important feature in Nick's story that the properties of the internal model, although they may, in some sense, as Paul would put it, they may map onto the physical world, the properties of that need not necessarily resemble the physical world. So if you have a forward model with a visual representation that predicts motion, it doesn't itself have to be moving. However, there are some cases, and I think space is an interesting example, where it turns out that, at least in primates that have a hippocampus, that there is a kind of spatial representation that is itself spatial, that exists as an inner model in the rat. So what you're looking at here is this. Suppose you have a rat and you put an electrode into a very special part of the hippocampal structures, the part called the entorhinal cortex. The entorhinal cortex normally just feeds into the hippocampus. So we're going to record from that. And then what we're going to do is we have a big open box. And we're just going to let the rat go into this box for the first time in his life. And we are going to record every time these neurons that we're poking, every time they spike. These red dots that you see are where the neurons spike. And these, although this is biology and hence it's all kind of rough, what you will see is that the corners and the edges and kind of triangles within that space are carved out by these cells. The rat's brain will do this regardless of whether there is stuff in this enclosure, whether the enclosure is completely empty, and whether the rat is doing this in the dark. In other words, it looks like the rat's brain in the entorhinal cortex forms a kind of grid of space. Now, I like this example in this context particularly because it gives you a sort of clear neural understanding of what an inner model is like in neural terms, so that it isn't a very sort of weird and abstract thing that might or might not be the case. By God, there they are. And they're called grid cells. They were discovered in Norway. And we now know that monkeys have grid cells, and we think that humans also have grid cells. And they are functionally critical. And sort of consistent with Andy's story, these are the cells that really enable the animal to do route finding, to know where it is, and so forth. Here's the other kicker. When the animal, when the rat or you or a monkey sleeps, often what you do is recreate your spatial meanderings during the day. So if it was the rat and he was running around a maze to find food, you can see by a different set of cells called play cells that fire when the rat is here and here and here and here, you can see during the deep sleep state that the rat's brain rehearses that. And it does so by putting those place cells in the context, or those places in the context of the grid that is its inner model. Now, this isn't necessarily an inner model that is a model that directly leads to what Nick wants, namely an awareness of certain sensory properties. So I'm going to let him tell that story, but basically the critical part of his story, and this is where I think I may have to get off the boat, is that there is a difference between sensation and perception, and that sensation is a signal about what's happening at the periphery of the body. And he thinks this is true not just for touch and pressure and temperature, which we would all agree I think is true, but also for vision. And I kind of doubt that it's really that way in vision. So think of the jellyfish. Couldn't be more simple, even simpler than C. elegans. The jellyfish turns out to have opsons, photoreceptors, and they clump. I mean, who would have thought, right? I mean, people were stunned when this discovery was made. But those photoreceptors serve the animal to predict what it should do when a big shadow comes along. So, you know, everything is nice, big shadow comes along, and it moves. So I think that in the case of the jellyfish, those photoreceptors are not telling the animal about its body. They're saying, as Andy might put it, here's how the heck you better move. That is, it's wired in order to do that. And I rather suspect that that's true in other cases of vision as well. And finally, it worries me just a bit that, and I think Nick has good reasons for this, and I just don't figure them out. He thinks there are 5 senses: smell, taste, touch, vision, and hearing. But I'm totally blown away by these other senses, not just the interoceptive senses, but also the vestibular senses. I mean, we know that they're absolutely crucial. We know that the kinesthetic senses are absolutely crucial to standing up. So there is this case, as you probably know, of a guy who has a peripheral neuropathy, so that there is no input from his tendons, muscles, and joints. So if you turn the lights on him, he falls down. And so we know from that and a variety of other cases that an important part of having a body, being the me that I am, involves vestibular and kinesthetic senses. But I think Nick has a slightly different way of going at the problem that leads him to want to say, let's just restrict the sensory information to these 5 senses. So with that, I'm going to turn it over to Nick, and I'll sit somewhere else.